We're here to focus on operations management, and I'm going to do a demo, I promise, and it will be live, and it may have some issues, but I've been pretty lucky so far. So my friend Shamil Patel, he had an event today. He did the first one, so this is a repeat session, so he won't be here, but he is our product management person. So if you see some things that interest you, but it hasn't gone far enough, please let him know. You can, his email address is shpatel@vmware.com, and mine is smcbride@vmware.com. All right. Here is the disclaimer. Everything I say may be wrong. No, I'm kidding. I think this is a general disclaimer. You've seen this all the time. It's just about, some of the things may change in the future after this presentation. All right. So let's get into it. So the first thing that I like to talk about, and it's kind of the art of operations management in your environment. We see everyone doing it a different way. We've seen it in our conversations with customers and these kind of discussions. But a lot of times people wait for a phone call and they'll just kind of search for the problem. So an angry person will call, or somebody concerned citizen will call, and they'll say, hey, I'm XYZ, and I'm looking at this virtual machine. This virtual machine is slow, and that's all they give you. It was slow, it's slow right now, or it's slow last night. And so if you're in this, it's kind of the least mature. I'm not going to say the least mature because we still do this every day, and it's actually one of the most reliable ways to do operations management is to wait for a phone call. And the reason that is because when you set up a tool like operations management, that tool is beholden to whatever thresholds you set in it. And those thresholds might be right or wrong for you, and they may be wrong or right for your customers. And we often have this situation where people will, I've been in a situation where I say, hey, I installed VROps into your environment. There's 1,500 alerts. What are you going to do about it? Right? I mean, everybody's probably done that. It's not unique to our tool. It's unique to all operations management tools. And the question is, well, I don't know. I don't know what I'm going to do. Matter of fact, given today, if my day is like yesterday, I'm just going to wait for the phone to call. Thank you for the tool. I'll kind of look at the lights and see what they look like, and maybe entertain when that call comes in, see if the tool agrees with it, and turn down the lights as I go. And that's true. As people first install a tool, it's very confusing, it's very complex. And my advice to that, if you're going to ignore alerts and you're just going to use it for searching for problems, then turn off the alerts initially, or get them to a bare minimum such that you don't have so much noise in the system. Use the tool to look for symptoms, and then as you develop those phone calls and that organic knowledge for your environment, train the tool to be part of this, to find the problems first. And so, again, the support call comes in, angry customer. He will call in and you use your search tool. The next evolution, or one of the next evolutions, is just to build a bunch of dashboards. And back in the 90s, we used to see this a lot. People would build NASA-like nerve centers, or NOC, Network Operations Centers. They started with network, but they soon evolved to systems management tools or operations management tools. And really, they would just come in and look, how red is my dashboard? If it's lit up like a Christmas tree and it's all red, I'm going to have a bad day. And that's all they would use it. It was kind of like academic. So they would have a team of people looking at this dashboard, and if it lit red, they'd go back to these following other ways, which is to go drill down on that red dot and see if there's any real problems and see if there's any phone calls that are associated with it. The next evolution is to build alerts on these dashboards. Don't wait for a human to look at it and do the search. Maybe build an alert. It gives you a threshold that drives more context to what is going wrong. So with a dashboard, you only have one dimension of data. You only have whether the system exists and if it's red. With an alert, you have other opportunities. I can generate an alert based on that one object. And within that alert, I can include contextual information like Okay, I see the CPU is high, but what was the disk I/O doing? Or what was the network I/O doing? So when I have alerts, I can build templates and build additional stuff. Now, we've been doing this since the 90s. In 95, I was part of a team, and we did an operations management tool, and we did thresholds and so forth. And there were a lot of still false alerts, like 1,000 alerts that we're saying. So with vRops, what we're trying to do, oh, I forgot. The last one is blind luck. So I wasn't really looking for a problem found me, right? This happens a lot. I'm sitting there just looking at the tool, exploring around, and blind luck, I find a tool and I actually am a hero for that 5 minutes. It can happen. So for vRops, we're trying to take this stuff and boil it down into something that's automatable, that helps you scale. When you get to 20,000, 30,000, 100,000 VMs, there is no way in your right mind you can even look at big visuals or 1,500 alerts and try to digest them in a day. So what I'm going to show you is a way that we're going from today and in the future of how to take these first basic concepts that we all know and start evolving them. All right. So how do we do that? Again, the tools that we use are important. So the first evolution tool with that phone call, you use diagnostic tools like ESXTops, perfmon, and so forth. Those are really good, but they're very reactive. And they're not part of your mature SDDC vision. The next one is basic alerting. I mentioned this before, which is taking what you saw in ESXTop, would it be contention, latency, high usage, high co-stop, some of these magic metrics that we're talking about, and I'll get into them later, and put an alert on it. The next level is correlated alerts. I mentioned this before. If I have CPU that's high, and I have disk I/O that's high, and they're highly correlated, meaning they happen at the same time, I can draw a better conclusion and route that alert to somewhere else. And in vRops, we are providing a form of correlated alerts. We can combine one or more using Boolean logic like ands and ors, and we can use not, like if CPU demand is high, but it's not disk I/O, I can do something different. Okay? Now, correlated alerts are nice. If you're just doing correlated alerts on static thresholds, then you're going to get whatever you put into the system as a static threshold. And a good example of this is disk space. Not all disk space being full is bad, right? We have Oracle. When you install Oracle on a virtual machine on a data store, we are going to pre-allocate all that space. Now, if we have machine learning, types of machine learning that we do are actual behavior versus expected behavior, and we call that anomalies. One is, so we look at the historical data of a metric, and we say if it has a cycle, it has one or more cycles, and we see that it's predictable, we're going to build a dynamic threshold boundary around that cycle, and if it exceeds that cycle, then we're going to say that metric is acting abnormally. Now, it turns out that one metric acting abnormally is interesting only for that one metric. It's not interesting for an entire object, like a virtual machine or a host or a cluster. But when you're measuring 200, 300, 400, 500 metrics like we do today on any given object, like a virtual machine or a host or a cluster, that when something goes really bad, they go bad in bunches. It's like a school of fish getting scared. When the shark is there, the school of fish go abnormal, and we see that. And we score the number of metrics that are misbehaving against the total number of metrics that we're monitoring for a system, a virtual machine. And when that gets high enough, we say that the object is abnormal and you should look at it. That's one type of machine learning that we do. Another type of machine learning that we do is simple forecasting. We take a metric like disk space and we forecast it into the future. We use all the history, whether it's cyclical or not. And if the forecast is rising, we have a time remaining score that's associated to the object. If it's not rising, then we say it's not growing or it's shrinking. So when we do the correlated metrics with machine learning, like time remaining, plus full, like space remaining, then we can tell you and weed out disk devices that are full but not growing. Okay, so that's one way to easily make your life easier. So we weed those out. And it's only through machine learning that you can do some of these. So another machine learning that we do is we do the stress. We calculate something called stress on any resource that a VM or VM or a host uses. And a VM host uses very similar resources like CPU, memory, disk I/O, network I/O, and space. And we build a container around special metrics or key metrics that we think are important to define a closed system. For example, CPU, the amount of CPU provisioned is the capacity. The amount that the hypervisor gave is called usage. And the amount the VM wanted, which is usage plus contention, is called demand. And so when we look at that in time, we can see if it ever needed the total amount that it was configured in the past 30 days or whatever time horizon that you want to use. Now, when you get past machine learning and correlated alerts, when you start combining them all, this is kind of where we are with 6.1. We have a rules engine that takes our metrics that we create using machine learning and combine them with the static or prescriptive understanding that you know in your environment. You can put thresholds on drop packets, for example. Drop packets is the easy one. You don't need to learn it, and that's actually hard to learn because it's supposed to be 0 forever, right? But if it goes non-zero, then it's something that you are interested in, and you can simply put a threshold on it, and if it goes non-zero, we'll do an alert on it or a symptom. So if you just combine all these, what you get is a way to look at 100,000 virtual machines using machine learning analytics correlated with static alerts or other machine learning analytics and give a recommendation that is specific to the problem that you're having. And when you get to this level, we call it being proactive. This would be in front of the phone calls, and actually you should be able to fix most of your problems before that phone call rings. All right. So this is an intro. This is some just basic definitions of some things before we get started on the demo. And I wanted to leave some time for the demo because I like to be a little bit interactive. I'll probably do 1 or 2 scenarios, and then I'm going to show you how to build some alerts and some dashboards and so forth. And we'll maybe ask some questions. So one of the terms that we've invented in VR Ops is this concept of demand versus usage. And I touched upon it, but let's slow down and kind of just look at it. So if the entire size of the bar, let's say, is the amount of CPU capacity that was provisioned to the VM. This is the total amount of CPU that if it's unconstrained, it could get. And we all know this, right? This is what we call provisioned capacity. Now, when you look in vSphere, they have this concept of usage. And when you look at usage, this blue bar, usage is what the hypervisor allowed the VM to get. Now, why does a VM not get what it wanted? Anyone? So other VMs, we call this population pressure. So this population pressure can come in various forms. It can be just general, I'm overpacked. But it can come in other forms, which is I have conflicting workloads. And what conflicting workloads are is that when I have 2 VMs that are part of a system that when I submit a query on let's say a web app, and that query goes to both VMs that are on the same box, and they compete for the same resources in the same millisecond. That happens a lot. People naturally deploy VMs and they go into the same cluster or box, and somehow they get put on the same host because we're not using affinity rules or any affinity rules properly. Now, what happens is because the average usage is low, and when I ask for it to work, it spikes, the system gets a little bit confused, and it says, hey, it's not worth moving these VMs right now because that spike was momentarily. But every time that spike happens, it's a blip in nature, in instant in time, and you'll get this contention that it happens well before you run out of provision capacity. And the right thing to do is not to resize a VM in this particular case. It is to figure out if those workloads are compatible and move them apart, or if you have what he described, which is general overpopulation. You don't resize a VM for contention all the time, you move them apart. Now, in layman terms, what we use as a metric of kind of describing where that edge mark is called entitlement. Entitlement is our fairness, or basically if you're overcommitting virtual CPUs, it'll say this VM is this size, and because of this size and the amount of other VMs that are the same size, I know you configured this, but you're overcommitted, so your dynamic entitlement is somewhere right in the middle there. And any time that the usage of the VM tries to go over entitlement, the hypervisor says, no, 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 we've got a fair share model here. You're not getting that because other people are competing for CPU, and you're going to wait. And that wait is called contention. So in CPU terms, contention is the percent of the time that the CPU was ready to run, or the VM was ready to run, but it had to wait. Simple as that. And the things that cause CPU wait are things like I/O wait. I/O operations can happen, and the CPU will be asked to wait for those I/O operations. It could be a swap operation where you didn't have enough memory and it shows up in the CPU metric. And it can be co-stop. Co-stop is another one where we overbuild our VMs. I have 4 vCPUs, or 8 vCPUs. These monster VMs are built, and they're put on a box with other 8 vCPU boxes, and essentially the VM just cannot find enough vacant CPUs to schedule this VM, because it has to schedule the vCPUs all at the same time. So counterintuitive to another thing about don't resize the VM, this particular case is the same case. Don't add more vCPUs to cause a co-stop, to resolve a co-stop problem, right? You want to see what is the demand of that VM. And if the demand of the VM is, the peak demand is lower than the configured, or a percentage of the configured, that I can reduce it by a number of CPUs, this VM will actually run faster because it's like a restaurant. It's easier to find a table of 4 than a table of 8. Okay, and you guys have probably heard this over and over again, but that's kind of why that bar might be red. All right, I kind of covered all these, so. Let's build this slide out. All right. So this is population pressure, and I did cover this, but the one thing that we need, I want to reiterate, is at the bottom. So you can see that when we visually diagnose a slide like this, we say that the big size is a provisioned. It says entitlement, but it should say provisioned. The big size is provisioned. The blue underneath is usage. It's how much it got right now. Contention is how much it wanted but it couldn't get. And if the VM has population pressure needs, you need to move the VM. So this if then else kind of statement is leading to how VROps thinks about these metrics. Each one of these bars is a metric to VROps: the provision size, the usage size, the contention size, and even the entitlement and so forth. And even the co-stop metrics and all those other metrics are part of our decision making. All right. So memory is a little bit different. So I'm going to build this out. So memory is one of those things where the amount of memory that I got for a VM can actually be bigger than the amount I want. And we call this over-provisioning. So things like we use 3 different models. In VROps, you can actually use any of these models to do capacity planning or operations management. The first one is allocation or provisioning. And so this slide is kind of showing that not only for an individual VM, but when you start talking about allocation and right-sizing, you can't right-size to allocation, right? I'm 4 gig, therefore I must be 4 gig. That's allocation, right? So you can't use allocation for right-sizing, but you can use allocation for stacking. So when I stack a bunch of VMs in a host, I can use an allocation strategy that guarantees I won't overcommit. And a lot of our customers are in this stage right now. They're very, very successful at doing their day job by not overcommitting memory. And essentially, they're using a success criteria of VM to host ratio, which has been very good for them for the last few years. Now, as we move on and we need to increase population density and maximize the amount of VMs to host ratio without buying new hardware, we're going to have to use a different model. The problem is I don't know exactly when the amount of memory I overcommit is going to cause a problem, right? Now, I can, inside a guess, figure out how much memory is going to be a problem, but by what? I can look at the amount of pages per second. It's pages out per second, right? When I do pages out per second on a Windows box or even a Linux box, what's often being paged, or almost 100% of the time, is the data that an application loads. All of the code, or DLL or EXE, is backstored by the DLL or EXE file on the system. So we don't need to page out that. But as I size a VM and it's doing pages out per second, I know that the code is loaded that it needed, but it couldn't load enough data to do its job, and it's doing a lot of paging to juggle that around. Now, if you have just not context switches, if you have page faults that are over and beyond just your pages out per second, that means you're page faulting for not only data, but you're also page faulting for code, okay? So we can resize VMs based on usage inside by understanding the inside, but we can also use usage outside. And the outside is what we're using for a metric is called active. Now, active is a unique metric that VMware created, and what it's presenting is not the amount of memory that was allocated. Okay, allocated is the amount of memory that a program will reserve so that it can write a variable or some kind of data structure. It first has to allocate the memory from the system, from the operating system, and then after it allocates it, then it can start stuffing data into that memory structure. So instead, active is the second part, where we look and we watch the virtual machine, and when the virtual machine is stuffing data into that memory that it allocated, we can actually see the amount of unique pages that it's touching. Now, why is this important? The reason this is important is as we move from the 80s to the 90s to now we're 2010, the way that we write programs has changed. We use programming languages like Java, Scala, and others that have garbage collection that do their own heap management, right? So if I look inside the virtual machine and I look at the guest OS, one of the things that I'm going to see when I type freemem is going to be that, lo and behold, the VM is using every bit of memory that I provisioned for it, okay? The problem with that is that I can set the heap parameters on a JVM to prove to you that I'm using all that memory. So it's hard to use in today's world what we used to use in the 80s and 90s, which was resident set size, to kind of show how much memory you needed for that application to run smoothly. Our best metric right now is active. Now, it has its own problems. One of the problems with active is that it's kind of a rate metric. Every 5 minutes, we look at how much memory the VM touched. Well, that's kind of a summation. So if in 5 minutes I touch 4 gigabytes, I'm going to report that you are using 4 gigabytes. Well, that speed that I touch is driven by the speed that I can touch, right? So if it's RAM, a modern computer can touch 4 gigabytes in, seconds, whatever. But once the guest OS starts paging, the guest OS will slow this active memory amount down. So from an outside observer, when we're looking at the virtual machine and we see the guests start to page, or we don't see the guests start to page, we see active memory go down, and we don't know. We think that it just is using less and less memory. Now, the way to get around that is to go inside the guest, and actually for vSphere Update 1, we have the VM tools that are improved. It will be available, post this conference, but I think it's in Q3. vSphere Update 1 with the new tools will give us key metrics inside the guest, which is the pages out per second and the context switches and the total page faults. And we can adjust our active rate to inflate that to show how much the VM used using active touch, plus how much it wanted to use, because we know the ratio of milliseconds to nanoseconds for page faults, and we know that a page fault is about 4K in size, and we know that how much memory that it usually swaps around. So at the end of the day, we think that active is going to be our best weapon into sizing virtual machines and knowing when exactly how much memory that you can possibly accomplish on a host. Now, it runs into problems as well. One of the things that we have is that right now, everyone is using consumed. Why? Because we invented this word consumed, and we map it to used in vCenter. It's not a bad thing. Consumed is a great metric. It tells you how much memory that was granted to a virtual machine and how much memory was reclaimed back through sharing, which is a nice virtualization feature. And it also tells you how much we gain back by compression. But it has some other bad things, like it doesn't tell you how much it gained back through page swap file through ESX, which is a really bad thing. But we can see that in another metric. And it also includes overhead. So we include, to show, the reason why we talk about all these in memory is that for VROps, we have all 3 memory models that you can, through policy, just check. So if you're comfortable with consumed, and that's the way you have your spreadsheets, or that's how you want to go to a tool and get you off the spreadsheet, then consumed is your one that you want to choose. You can also turn on this active at the same time. You don't have to do either or. You can do all of them. And what that gives you is a way to say, okay, I like consume, but balloon is going to lower consume, so that's going to hide some issues to me. So I'm going to combine it with allocation and know exactly how much forecasting I have. And then I'm also going to back it up with usage to see that demand model. All right. So that I'm running out of time on my presentation, but I want to go to the demo and show you guys how we do this in real life. I will pause to say, is there any burning questions? I don't want a lot because I know people want to see a demo, but is there anything that I presented that people need to ask right away? Nothing? Okay, what do you got? Can I repeat the definition of consumed? Certainly. So the amount of memory that's consumed is the amount of memory granted minus ballooned minus shared plus overhead. Okay, and there will be some swapped instead. If you're swapping, there's swap in there. Please don't swap. None of you guys swap. ESX, when it swaps, it halts the entire VM because the VM is a process. even all its vCPUs and everything. It's a process, and it has no alternative but to swap. There's another kind of takeaway is that there's this notion that Java VMs and so forth are really hard to manage, and the fact is it's true. And it's not for what you think. There's been talk about garbage collection and some other things getting in the way it manages memory. But we don't care from a virtualization who's managing the memory. We don't care if it's the operating system, Java, a database, what have you. We always see that they're touching memory, and that's why active is really good. We can see if Java's touching memory, if the garbage collection is working, then we kind of see it touching it twice, so it's more conservative. It's not a big deal. But the problem is that because these things manage their own memory, when they boot up with the understanding of how big the VM was provisioned. So if I provision a VM of 4 gig or 16 gig, and I run Java inside it, or I run a database, it's going to say, oh, I see a 16 gig VM. So therefore, I think I can use this much memory, and my max heap size is usually configured to something reasonable to take all that memory, and so is the min size. When the balloon starts inflating inside a Java VM that's configured as such, the problem is that any inflation of that balloon can cause pagination. Because Java's got its thing, and the balloon is inflating in this little closet called the operating system. And when the operating system can't work, Java can't work. So the file system cache is suffering and some other things. So that's one thing to take away from consumed, and that's one thing to take away from Java loads. Okay, so all right. So one of the things that we'll just start with, which is this is VROps, all right? When you open up VROps, this is what you see at the beginning. You see a general health, risk, and efficiency. We use health, risk, and efficiency to determine the urgency of a problem. Health is used to denote that it's worth calling someone in the middle of the night. That's how you should think about it. Now, would I call somebody for some of these alerts? No, I'm giving a demo. But disk space, on a critical app, yeah, I would call somebody. We need to either resize it, or if I am empowered, I would do it right now. But the fact is, it's out of disk space. The application is going to imminently fail, and I need to do something about it now. Risk is another one. It denotes something that it needs attention, like a meeting. Now, usually risk is more in the lines of capacity planning. So capacity planning is more about stress, and here you can see hardening guidelines. You're at risk. Nothing's going to happen right now tonight, but you guys should have a meeting next week. It's worth having a meeting. And then efficiency is opportunistic. These are things that you want to do instead of buying capacity for capacity remaining in the risk column, and maybe go clean up some oversized VMs or idle VMs, take them off. Now, if I am here and somebody is asking me, oh, wrong laptop. All right. So I talked about if somebody calls. So I'm going to do a real simple exercise. In here, this front page is your active alerts. These are the things that are active right now, meaning I can go there and that disk space will be out of space right now and I need to look at it. In the other cases, I have non-active alerts. So if somebody calls me about a desktop, so let's see if I can find a desktop. And I've been talking a while, so let me just make sure I didn't get logged out. All right. So somebody's called me and says, look, I'm having a problem with this desktop. And I tell them, I don't have any alerts right now. When did this happen? Well, it happened last night, or it happened, on the 27th or sometime last week. And and something's wrong. So what I would do is I would go to that desktop, since they told me they were using this desktop, and I would say, okay, well, let's go take a look at some alerts. So I look at the alerts for this desktop, and you have no alerts right now, but maybe you have some alerts in the past. So I clear the active filter. I say I cleared them. I said I clear them. Okay, they were there yesterday. Somebody cleared them. Yeah, it's not the case. So let me just make sure. Well, this is the beginning of a bad day. All right, so what's supposed to happen is I have some alerts on drop packets actually on this, and I don't know why they're not there, but let's go take a look at some drop packets. I don't know why my alerts all of a sudden went away. Let me just check this other RDP session. It's not the first time I've had a problem here. Okay. Got my password? Yeah, I got my password wrong. All right, since we're over here, let's just take a look at network. Okay. So if I want to look at the network, usually I look at virtual machine network diagnostics. And in this particular case, I have a view called trend. So generally, I'd have an alert for this. I'm not sure why it went away. But indeed, I have a number of packets transmitted. This is packets received, packets transmitted, received packets dropped, and we have transmitted packets dropped. And in this particular case, I can say, oh, look at one day. But he said it was maybe last week. So let's take a look at weeks. And I don't care about packets received and transmitted, but indeed I do see received packets dropped and no transmitted packets dropped. And that's just because it's a green line and I see it go up. So, and in this case, I see 4,000 of my packets were dropped at some point. So this was him trying to use an RDP session to this particular machine, and he has dropped packets. All right. What I wanted to show you on that alert is how we combine symptoms. And so let's take a look at where that packets drop takes you. So I will go to the alert definition, since the alert instance didn't show up. And I will type drop. Nice caps. Virtual machine. And so here, what I want to show you is the difference between these variances. So I have virtual machine experience high number of received packets drop. Virtual machine experience high number of virtual machines packets drop due to high CPU. And virtual machine has experienced high number of transmitted package drop. And why is that important? So when I go and construct my alerts, if I go edit this alert, we'll look at the symptoms that are being used to generate this alert. So in this particular case, I've got two symptoms. I have one symptom that says virtual machine receive packets drop. I have nothing about number of packets coming in. And the virtual machine CPU demand is not, the red not symbol or do not enter symbol is highlighted, and it says, I do not have a CPU demand issue. So the reason why we have those two symptoms constructed like that is that you can link it to a knowledge base or give a recommendation. In this particular case, the recommendation said, this is a well-known issue. When you're not starving for CPU and you're using VMX-NEC3, it's an issue if it only occurs on 2 to 3 virtual machines, which it is. It only happened on one. And it only happens when the CPU performance is not that high. And what happens is it turns out that Windows comes with a very small receive packet buffer. And the recommendation, let's see, is to go to Device Manager Properties, change the value, the default value is 512, please make it to 8192. So this is I started with a very basic example, right? This is something that everybody can kind of see. They say, okay, I see a bunch of drop packets. I can see that there is no CPU demand, not enough CPU demand to cause a problem. And we can give a recommendation to do something different. That's what this is. Okay, so let's go to another one. So I should have some problems coming now. Let's say I have another problem. And that problem is around CPU. So I have one problem here that says CPU machine in a cluster is demanding more CPU than its entitlement. Okay, that is media. And I have another CPU cluster has CPU contention caused by less than half of its virtual machines. These are kind of two different things. The reason that we have this less than half of the virtual machines is to kind of show this population pressure issue. So let's kind of go look at that one. So if I go look at this box, I look at the alert details. It reiterates the problem. Half or fewer of the virtual machines are overloading the host. This is kind of the villain problem, right? The recommendation is to use some kind of migration or vMotion to move these VMs with the CPU workload to somewhere else to isolate them such that the other people can be happy. If this were all the vCPU, every single VM that had high demand, then the recommendation would be something different. It would say resize a host, make it bigger for these VMs. And so let's go take a look at this definition. So this takes us over to the content. This is the alert definition. By the way, this is supposed to be how the drop packets was supposed to work, but it didn't work. So we have this alert definition summary. You can put the name and so forth, but the unique thing in here is that we have self on the host system, that I have a symptom. Base objects exhibits all of the following system. The host is inside a cluster. The parent cluster compute resource. So this is saying my parent cluster, that all the parent cluster compute, any of the following. So this is not DRS automated, and it's not DRS enabled. Why is that important? Because if we had this situation where one VM was causing a problem, DRS will take care of it, right? In this particular case, I'm finding a host that's inside a cluster that is not DRS enabled. And I go down. If the individual host has CPU contention at a critical level, or immediate, any of these regular, just any CPU contention is how you can translate that, and the population of virtual machines is true when less than or equal to 50% of any child has CPU demand at a critical level. So what this is saying is that only smaller than 50% of the VMs have demand that's high. So we have these bad apples here, okay? And then you can, it continues. And then the recommendation is to vMotion. Now, if I want to add more symptoms to this, I could. The way that you do that is you simply go find a symptom, and you just drag it over, and you can just put it in there. That's how we build alerts here.
What would the recommendation be? Do vMotion or add to DRS?
Okay, so the question was, why would the recommendation only be to move or migrate and not be to enable DRS? Okay, so in this particular case, out of the box, we just put it to where if you have DRS enabled false, we think you have a reason. In this particular case, there are cases where we do recommend DRS to enable, and we can augment this to turn on DRS. So that's a good example of going to the recommendations here, this particular area. And we can find DRS. Oops. If I can type. Turn on DRS. So I can simply say that this is the first recommendation. Don't do that, please. I'll just drag this guy over here and make him the first recommendation. So this is a good example of changing your recommendations on the fly. And you can add them, whatever your policy is, we provide something out of the box, but you can always add it. And one of the things that I like to show off is that hot link to that KB. That's why I picked on the drop packets. You can do a hot link to a wiki inside your environment or a SharePoint in your environment that is a runbook of things that it can do, or you can do it to knowledge bases. We do knowledge bases out of the box because wikis and SharePoints are personalized. They're about your policy. But of course, you can add them.
So if your recommendation was to turn on DRS, at some point you're going to have an action enabled to do that on VROps without having to go through user?
Yeah, the question was, can we turn on DRS automatically when we detect that is off and not that you're entitled to it? We don't have turn DRS on right now. We will. Our available action out of the box are pretty extensive, and we do work with vCenter directly, or you can go through VRO, vRealize Orchestrator. And so let's, we got about 5 minutes, and the only thing I want to kind of show you, maybe, is to go back. I wanted to go back to this alert. One of these alerts, which is kind of nice here. Looks like we have a disk IO alert just happened. So on this alert started on August 30th at 10 at night. And all this data that is about this alert is 6 hours prior to this alert happened. So what we want to do is bring the data that is in context of this alert so that you can help diagnose. And if you see across the top, we have, basically which objects are impacted. These are other objects. You can see a timeline of when these alerts started happening, these symptoms and alerts. So here we can see that I got an alert for the CPU, and then it gets objects and so forth. If this is within a cluster, I can actually bring in objects from its parent or its descendants, these symptoms. I can even see the relationship of this object to other objects and see their health state. So I have this virtual machine who's part of this data store on this box. You can see the health of this box is fine. So in this particular case, I got a virtual machine that's not really causing problems to the parent, but it's causing problems to itself. And I have some other machines that have health issues on top. One of the new visuals at a glance that we provide that's very similar to this. So this media one, the alert was about a resizing event. So it's saying that you have chronic CPU issue on this virtual machine. And that's very different than having a spike or unexpected spike, which we have alerts for that as well. So I have alerts that are coming up now for disk I/O because I turned on a benchmark. And I have alerts, contention, running out of disk space. But what I wanted to show you is this new visual. And this new visual kind of is focused on just the art of right sizing. So it's split in three. It's got underutilized, somewhere optimal, and then anything in past the red is overutilized. And what that means is that you need to resize these or something. And if I highlight over these, you can see that this particular machine has got one vCPU. We recommend 2 vCPUs, and that's because of chronic CPU usage. It's using all that. And it needs a little bit more memory. I'm not that amount of memory could be inflated, but you can go through all these, 4 gig versus 4.1, 1 versus 1.2, and 1 versus 1.2 again, and so forth. And then if you go all the way to the left, these virtual machines are idle, and we recommend to just remove them. These are virtual machines that are using CPU and memory that they're not doing any work that we can tell, but they're overhead, so shut them down and get rid of them. All right, so we have 2 minutes. Now, I do have some other things, but I don't think we have time. I would like to answer 1 or 2 questions if there's anything. Maybe I'll ask a question. So what's your your biggest pain point? Is it disk I/O? Disk I/O? Memory? Memory? So disk I/O and memory are the most, you said performance, but when I say performance, disk I/O and memory are usually the ones that are a problem. And I think they are the ones that are hard to look at. If I had time, I'd show you how we do disk I/O. Disk I/O is kind of very unique in our system. We kind of learn the capacity for a given app on a VM, how much capacity IOPS and kbps that we think that system can use, and then we tell you when it's reaching that capacity. So it's kind of unique. All right, thank you very much. And if you have questions, come up here. I want to let everybody go to their other one. Thank you.